Okay. Yep, started. Okay, awesome.
Okay. All right. So the quick high level, there's a few corporate slides that SNC likes me include, so I'll hit them kind of quickly. The big piece here really is it's a privately owned company. It's been owned by the same couple since 1994. And that's kind of nice because it allows us to plan a little bit further out on the calendar than some of like the publicly owned companies that have to battle from quarter to quarter. We're fairly large, about 5,000 personnel and 40 offices kind of around the globe, mostly centered in the US. Our three major business areas, national security and defense is really the largest. We also have space systems. We develop a space shuttle. We're now partnered with Jeff Bezos's Blue Origin to develop a orbital reef, kind of a commercial space station. And then we do a fair amount of commercial solutions as well. Then kind of diving into the business area that I actually work in is mission solutions and technologies. So SNC is basically split into two areas. There's IAS, which focuses more on the integration side of taking other people's technologies and putting them onto platforms. And then MST, where we largely develop our own technologies, but also integrate technologies from other places. And a lot of these areas are really starting to identify, and this is something I'm really pushing for internally, how much machine learning, computer vision, robust and resilient autonomy are going to be just critical kind of moving forward. And it's going to be some of the first stuff I kind of immediately move into. First, though, I did just kind of want to briefly just kind of summarize. Oh, is that video not playing? Okay. Summarize my background as well. I haven't gotten a chance to meet most of you, so this is kind of my chance to address the group or introduce myself to the whole group. My background, I have a bachelor's and master's in mechanical engineering I got from University of Nevada, Reno, a few years before Petros joined, but the same school. And then I went up and did my PhD in robotics from Oregon State University with kind of emphasis on distributed multi-agent coordination. And you can see this is one of the projects I worked in. I started on this one in 2012, so quite a while ago. Getting teams of quadrotors to autonomously explore subterranean spaces and map them. Single robots, we got that working pretty well, and then eventually pushed up to doing a team of three exploring the space. And it was kind of nice because this kind of helped lay some of the groundwork for the DARPA Subterranean Grand Challenge, which then SNC was fortunate enough to be on the team with UNR, which went on to win. And just very fortunate to have amazing partners on that one. In addition to that, and part of why I kind of moved into the defense industry, is I spent 13 years in the military, which has been kind of a nice mixture. I have a lot of practical hands-on experience working with a lot of these ground systems that I'm now kind of working with, and then direct interaction. I've had aircraft overhead actually kind of save me in some of my operations that I did. Since then, I kind of joined SNC in 2018. I'm now a principal systems engineer, and I kind of sit on two different groups within MST, which is, again, is kind of half the company. So I'm on the MST technology team, where I kind of help guide new technologies and how they're deployed across the various product lines. And then the MST systems architecture group, where I help kind of architect what the larger systems look like and kind of plan into the future how all the systems will work together. And as a big part of this, what I do is leading internal and external science and technology efforts, with main emphasis on robotics, autonomy, sensor fusion, and those types of things. So with that, this kind of gets us into NASA ULI. We're here, the technical challenge for SNC is really focusing on the testing, evaluation, integration towards technology transfer. And initially, and it seems like there's kind of an ongoing discussion as to how SNC's role might change in this, but initially, we're focusing on developing a photorealistic simulation environment. That was primarily organized around our DVEPS helicopter, which I'll kind of talk about in a second. And that was going to include doing a realistic and relevant environment, showing the platform, a subset of the sensors that are available on it, and then kind of a flight physics model, and then merging them into a relevant concept of operations. So a lot of these helicopters regularly do operate in urban environments, as well as kind of more open environments. So just kind of showing how these same technologies that all of you on the team are developing could be applied and transferred into this domain. And then now there's kind of an ongoing discussion on how we could take this a step further by leveraging one of SNC's UAVs. It's called the Volley 10, which is a test platform for one of our real systems called the Vol-ET, and show how these same technologies that all of you on the team are developing can be applied on an actual UAV that's outside of a strictly research environment and kind of put through its paces and kind of really show a pathway to get it transitioned onto products that are actually out and being fielded within the DoD. So it's kind of the introductory material. So kind of moving through next, the three things I'm largely going to focus on is first kind of motivating the robust and resilient autonomy. And part of this is just kind of getting at why I think this is such a critical effort that all of you are working on. And then I also want to point out a couple obvious immediate extensions that I see are, I think everybody on this call probably has a way to kind of contribute. And these are problems that with the DoD is trying to solve right now. And I think it'd be beneficial just kind of raise awareness. Next piece, kind of run over a little bit more detail of what we did during year one, focused on DevEps integration and the direction we were heading, and then kind of revisit the transition of Volley 10 integration. And anybody who's on the TC4 meeting last week, there's going to be a fair amount of repeat in here, but some new stuff. So I do kind of apologize for a little bit of the repeat there. Well, to motivate the RA within the DoD, I just kind of want to point out something that might not be obvious is basically every system that the DoD has is currently reliant on a combination of GPS and or active RF emissions. So we really use GPS to figure out where basically everything is, do all of the command and control, and then there's not many truly autonomous systems yet. For the most part, they're all actively controlled by a pilot remotely. Nothing's actually fully autonomous yet. And the main problems with this is GPS and communications are easily jammed. Anybody paying attention in Europe right now can kind of see the battle that's going on there to addressing this. And one of the other major limitations is any active communication sensing gives away your location, which is not ideal when you're in a potential hostile environment. So in parallel to all this, there's a large push towards moving everything towards unmanned systems. Kind of jump into the bottom, but right now there's a major push to develop autonomous surface and subsurface vehicles. 4 out of the 5 the next generation ground platforms that are being built are optionally manned or unmanned. So the future of the Army, which I honestly thought would be the last one to go, is now clearly pointing towards fully autonomous systems. And then now there are still, of course, manned aircraft being made and produced, but traditional UAS are taking a larger role. And there's now programs across multiple countries looking to develop tens of thousands of small UAVs. So within the DoD, globally, everybody has kind of acknowledged that unmanned systems are going to be the future here. And that's really hard when you can't depend on GPS or an RF link to an operator, because the obvious solution to counter all of today's unmanned systems is just electronic jamming or electronic warfare systems. So for these systems to be able to actually work, they really are going to need robust, resilient autonomy, which is why it's really I'm thankful to kind of be included on this effort. Now, a hard part of this is when these systems are being fielded, they're going to be fielded in quantities of thousands of potential systems. So things really do need to be robust. They need to work all the time. They can't fail at any appreciable rate. And part of the difficulty of that is it's still kind of an open problem for how you can verify machine learning. And I'm happy to see that that's part of the effort that's going on here. So 2 of the, I'd call them lower hanging fruit kind of opportunities is develop automatic landing systems. Currently, SNC and Lockheed, plenty of others develop automatic landing systems. And these, effectively for manned and unmanned systems, they provide precision approach. So they actually pick up the aircraft about 2,000-ish feet out, kind of varies from platform to platform. Automatic taxi, so moving them around on the ship or runway, takeoff and landing can all be done remotely controlled of both manned and unmanned systems. So most manned aircraft now, they're landing on aircraft carriers. The pilot can take their hand off the stick and these systems will automatically fly them in. As an example, like SNC's performed over windmill and landings without major incidents, and I'm sure Lockheed, Boeing, and others have similar measures of success. And all of these use a mixture of technologies. So differential GPS is a big one, and then the other piece is radar. And the kind of problem with this is all of those are effectively dependent upon GPS that can be jammed and emissive radar that can give away your position. I've been told you can detect the emissions coming off of most of our aircraft carriers all the way from space, like the ISS is able to detect them. So being able to hide them is effectively impossible with all the current systems that they have. And getting these to be fully functional to switch to something else, which a lot of this is pointing towards how you can use machine learning, computer vision to do this type of work, is going to be a little hard when you have to have really high confidence bounds. So for example, on our systems that have our landing manned aircraft, it's required the probability of failure is 1 in less than 10 to the minus 7. And it's going to be really challenging to kind of get some of these a machine learning based solution to that level. And I honestly see that the work this team is doing and some of the conversations we had a week ago, moving in this direction. It's just that bar is definitely set high, and it's definitely work that there needs to be more work pushed into that space. And then kind of the other piece is that verification also needs to run real time on swap-C constrained systems and safe hardware. And one of the things that surprised me switching from academia into industry is just how limited some of the constrained hardware is. So for example, on truly mission critical systems, which we call data assurance level A or DAL-A, they only very recently approved multi-core processing. And if you think about that, most of the things that are being done here, where you're talking about interloop controls, would fall under that higher level of verification. And if you're if you're dependent upon the perception system as inputs, those could potentially also fall under DAL-A, and getting those to run safely on that hardware would be difficult at best. So I think there's work to be done on the verification side, both on the software and also the hardware, to be able to make it run on all these systems. And then kind of the other piece is landing on a ship is really, really hard. So this video right here is actually the first time a autonomous ship actually landed on an aircraft carrier. It was nice. SNC developed the system for this. But what was, I did really quick, but this was kind of fun. We got the, after these systems ran for a while, one of the complaints that we actually ended up getting back was the fully autonomous landing system is too precise, and that wheel, when it touches down, it was hitting the same exact spot every single time. And that was leading to the small patch in the cable where it was getting caught by the hook, and also on the deck kind of being eroded over time from just constantly being hit in that one spot, which is just kind of a cool problem you have when you have like a really high-performing autonomous system. But anyway, so landing on a ship is really hard, and the ship largely is moving under its own power at a fixed speed and heading. But when you start getting into some of these higher sea states, which is kind of a measure of how much the boat is moving due to the wave motion, the touchdown point of where you're trying to actually land the UAV onto can potentially be moving up and down about 2.5 meters, so 5 meters total of vertical travel, and rolling plus or minus 10 degrees. So they're a absolute roll of 20 degrees across the span. And you think about this, you start approach from typically around the ballpark of 2,000-ish feet away. It's, of course, will depend on the system. Being able to hit that touchdown point that's moving at that speed using just cameras, you have to start tracking the ship's motion, and you have to start being able to do that from fairly far out to be able to adjust the flight on the way in to be able to hit that touchdown point. Currently use a mixture of onboard and offboard sensing to be able to send the ship motion back to the UAV, but it's kind of using just a simple passive camera-based approach is going to be challenging, but doable. There's definitely a fair amount of work going on in the space. Then the other piece that kind of ties into the control side is, as the ship's moving, especially through poor weather, all the superstructure on the back of the ship, which you can kind of see in the video again, leads to basically airwakes coming in behind it, and the UAV has to be able to respond to that in real time as it's coming in, and it's not going to know in advance what those air wakes are going to look like. Well, the kind of next and last kind of opportunity that I'd point to is aerial refueling and docking. So a lot of these currently primarily used for aerial refueling. This is a picture from the first ever aerial refueling of a manned aircraft. You can see there, both pilots' hands are up in the air while they're doing the actual docking. And these typically use a combination of GPS and INS, or RTK GPS really, combined with computer vision. And here, while it's nice that computer vision is inside the loop, it's strictly bounded by the GPS INS solution, and it's used continuously to verify the system performance. And there really is a desire here to remove that GPS dependence and active emissions, so the communications back and forth between the ship, and having this ran strictly through machine learning computer vision. But there's a lot of those same safety concerns you have for the aerial landing side for doing this with the airplane. And some of the complications here are that you end up being kind of a coupled system where you have, as the carrier is moving through the space, its motion is of course affecting the drogue that's being dragged behind it. You can hit different wind patterns, which can cause the drogue to kind of move around unpredictably. And then also the motion and shape of the system that's actually doing the docking. So the UAV or the manned aircraft, as it gets close, it kind of affects the aerodynamic forces acting on the drogue and causes its motion to move around. And all that kind of needs to be tracked at a high rate, and it needs to be tracked with very high confidence, because once again, you have manned aircraft inside the loop that could be affected if something were to go wrong. And a lot of this has historically been used for air refueling and manned and unmanned systems, but now we're starting to see, there was a recent DARPA program where it was used to deploy UAVs out of the back of a C-130. They would fly around and do their mission, and then they would go back and then re-dock and be pulled back into the C-130 to be refueled or refitted with different sensors, what have you, to be able to fly around, with basically trying to turn the C-130 into a mobile aircraft carrier. So that was kind of the initial introduction, so motivating the robust and resilient autonomy and some extensions that I kind of saw. Next, I'm going to go over some of the DVEPS focused integration. So I feel like I have these slightly out of order. Okay, so this is the DVEPS system as of 2016. The current system we unfortunately can't really show videos from, just because it is a DoD project, but this is from a while ago. It has improved quite a bit since then. Oh, let me turn the camera off, sorry, the sound. And what you're effectively seeing is the helicopter is flying into this environment. And here it's using a combination of infrared cameras, radar, and LiDAR to create a 3D map of the environment as it's flying in. And what's actually being displayed here is not actually the IR image. This is a synthetic view into a 3D world model that the helicopter is generating in real time as it's flying. And the benefit of this is, as the pilot gets kind of browned out down here in the bottom right, and they're unable to see out, they can continue to track their motion as they move around inside this space. And what surprised me about this when I came to SNC is one of the problems that was typically a struggle when I was doing my robotics work at Oregon State was trying to develop this a reliable 3D world model to do the path planning and decision making inside of. And it was very surprising to me to see how mature this was. And I thought this would make a good program to kind of push this efforts towards as well, because it meets a lot of the perception needs, or it aligns very well with the work that's being done inside of NASA ULI. And then the other thing I would kind of point to is when you get to this point, or why this is such an important problem, is when you end up in this environment here where the pilot's completely browned out. Helicopters are typically very top heavy and fairly narrow from side to side. So lengthwise they're fairly stable, but side to side they're fairly narrow. And when you end up in this environment, the pilots frequently can't keep track of how well they're able to actually what their lateral motion is. And if they just catch a rail on the ground or come into when they come in and land, it takes only a very small amount of lateral motion for the helicopter to tip, which can cause the propeller to strike the ground, and then it's a catastrophic equipment failure and often leads to death of everybody on board the aircraft. So coming in this environment is typically very dangerous because they don't have this view. So the original intent was just to provide this view, but now kind of pushing to see what else is possible using this 3D world model. So the way that it's made is it takes a combination of offline data, so DTED, Buckeye, which is LiDAR, and then other databases, and fuses it into a world model in advance. Then as the helicopter flies through the environment, it uses the onboard sensing to update that model, which is then updated continuously throughout the flight, render a display of it, and then fuse in any symbology, and then present it onto the pilot. And that's effectively kind of the workflow through there, put quickly. And one other thing that I would kind of point to is this solution right here. And something to kind of think about is originally it was developed in mind to use this specific radar that we developed. But once you actually start integrating stuff into the field, you have to start modifying everything to work on different platforms. So when you're developing these systems with the intent of transitioning them, you need to be aware that the sensor that you believe might be the perfect sensor is often not the one that the customer wants on their aircraft or the one they can afford on their aircraft or anything else. So a fair amount of effort needs to go into expanding the system so it can work with any potential 3D sensor that comes in, even of different modalities. So radar has a benefit of being able to see through dust while LiDAR can't. And LiDAR provides a higher resolution data, which is great, but just causes various problems. And then also same thing with IR cameras, inertial sensors, GPS. So that's one thing I would also say as you're looking towards transitioning capabilities is really kind of focusing on the ability to make it work across a range of different hardware, because every platform is going to bring their own different hardware that things need to be applied onto. And then one more kind of piece is when we do a lot of these types of work with cameras, LiDARs, radars, and other sensors, it's typically we require that the systems be highly calibrated. We need to know the extrinsic and intrinsic calibration as we're flying through the environment if we're going to try to do anything with a mixture of 2D and 3D information. And what we found is very frequently it did not take too hard of a landing for the sensor calibrations to all go off. And typically it's a manned operation where you have a series of set markers to go through and redo that calibration. So one of the things that we had developed, and I would encourage you to also think about, is being able to identify as part of that verification process that the calibrations have changed, and then having something in place to address those calibrations and recalibrate in mission if at all possible. And a lot of this is dependent upon having GPS available, which might not always be an option, but at least it provides some means of, while in flight, to actually continue the mission and use those sensors effectively. So within the NASA ULI effort, our plan was to basically modify some of our existing simulation environments built on Unreal and ROS, which is nice because it aligns with the simulation architecture the team's already using, to see how we can instantiate the DVEP system inside of that environment to test the RA pipeline on. At this point, we have we got to the point where the Unreal simulation environment was stood up. We were able to use either an environment that's based on cesium, which is nice because this includes real world locations with some mixture of terrain and buildings. The building footprints have improved drastically recently. For anybody not aware, cesium partnered with Google Earth to be able to pull in other locations. SNC also has commercial partnerships with Maxar and other companies, so we own areas around Reno, Nevada that we could make available to the team. And then as part of this, as part of the simulation effort, we also simulated the cameras on board, a subset of the cameras on board the helicopter, as well as some of the other various sensors. You see here kind of one of the pictures from inside of a simulation environment. This is not a real location, it's a synthetic environment. And then provided a helicopter aerodynamic flight model and a kinematic flight model to kind of simplify the integration and testing. Here's what our simulation architecture primarily looked like. So everything was running inside of Ubuntu, I say 2004, but I could be mistaken on that. Unreal, And then we effectively have Unreal publishing out ROS topics and then ROS subscribing into it to make room for the helicopter controller. We started looking at integrating inside Guam. We ran some initial tests. It seems like processing time, the polynomial model should work just fine for us. We did a little bit of initial testing. That was offline to show that we could bring in the Guam data and then replay it inside our simulation environment. And we're going into the process of trying to get those connected together when the changes basically happen. Let me get that going. So here you can kind of see this is the default Guam hover to transition model. I don't remember off the top of my head if this is from the polynomial model or the I believe it's blade theory model. I'm trying to remember. It had an S in the title, but anyway. And here, this is basically showing the data working inside of Unreal and ROS in parallel and matching the flight profile. So the next step that we were starting to work on was sharing data between ROS and MATLAB in real time. Just gonna let that finish really quick. But while we were in that process, I had a few meetings with some members from UIUC, UNR, and some of the other partners on the team, and we kind of revisited the transition opportunities and wanted to see if there's a way to better align with some of NASA's objectives in the space and really focus on that technology transfer piece. And it brought us back to this slide that I showed earlier in the year, where SNC recently acquired Valancy, which is this made this UAV down here, and is developing a vertical takeoff and landing UAV in support of a few DoD efforts and some emerging commercial opportunities. And we have started the conversation to see if it makes sense to continue in that direction in DVEPS, or if we should transition over and try to do actual flight testing on board the Valancy. And it appears we're still in the middle of that discussion, but yeah. So the next part will largely focus on the new transition onto the Volley 10, and it's basically this is kind of the proposed plan for how we could integrate onto the Volley 10, do the integration with it, and the type of testing that I think is relevant. We've kind of discussed internally as a team last week. So just a little bit of background. Valancy was founded in 2015. They're a small venture-backed company, though they did raise about $75 million of funding. And SNC purchased them in 2022. So what you can see here is this is called the Volley T. It's the larger Valancy aircraft. It has 8 rotors effectively for vertical flight, and then a big pusher prop for horizontal flight. From this, they have 3 platforms: Volley 10, 20, and 50. The Volley 50 has become the Volley T at SNC, and the main point of these is long-haul hybrid flight. So 10 to 50 pound payload options, the 50 to 350 mile range. And some of the emerging opportunities we're looking at is ship to ship and ship to shore cargo transfer and resupply. And then they've done a fair amount of other stuff for disaster relief and commercial logistics around the world. So this kind of overview of the Volley T, which is of course the larger aircraft. It's a hybrid VTOL. It really does kind of focus on the modular open systems architecture that the Air Force and really across the DoD is kind of pushing to. It is built on the predecessors, the Volley 10 and Volley 20. It's, as you can see, pretty large. It's about 24-foot wingspan. The minimum takeoff weight is 275 pounds. I've been told that that's with barely enough fuel to get it off the ground, but it can go 400 pounds is what it's rated to. But the limiting factor there really is the landing gear, and it can go quite a bit beyond that with the thrust capacity that it has, which of course would increase the payload weight. And then endurance is about 9.5 hours, and then it moves pretty fast with a cruise speed of 57 knots. But this system, I'm told, is on the order of $1 million a piece, and I asked, but it seems like it'd be pretty challenging for us to do test flights on it. But what I have been able to do is I'm getting a Volley 10 delivered to Reno, Nevada, or Sparks, Nevada, really, in mid-January, early February timeframe. And it's the official Volley test development platform. It uses the same autopilot, obviously tweaked a little bit to work because this is a quad rotor instead of the oct rotor, but fundamentally most things are the same. So it's obviously smaller, though still fairly large, almost 10-foot wingspan, takeoff weight 55 pounds, 90 minutes max, but with vertical takeoff and landing, more like an hour's realistic flight time. And then the cruise speed is pretty fast. I was kind of surprised by this. It's cruising at 56 miles an hour and then stalls out below 45. And then on board, the power system for it is about 60-volt DC. Then for the flight controller, we use the ArduPilot. It is modified, but largely it's a variant of the latest stable version. And I was kind of excited to see this because that does make it seem like it'd be fairly simple for the team to integrate with and actually perform flight tests on, because ArduPilot, of course, being open source, makes it a little bit easier to share code and move software around between us. As part of the proposed integration flight plan and kind of the direction I see this going, or would like to propose this going, of course, I would very much would like team's feedback on this, is SNC would develop the Volley 10 simulation. We're expecting that to be somewhere in the order of 6 months. Internally, we're already using JSB Sim for pre-flight checkout of the Volley 50. Unfortunately, the Volley 50 model is controlled unclassified information, so I can't share that with the team, but we are working to modify the Volley 50 model to do a Volley 10 model that we can then make that available to the team. And JSB Sim is an open source flight dynamics simulator. You can pull it from GitHub. Should be fairly easy for anybody on the team who is interested to stand up a version of that. At the same time, so with that, SNC will develop the Volley 10 JSB Sim model and integrate it into our Unreal ROS simulation environment that we previously had set up for DVEPs. And then we'll provide the model, which hopefully should contain all the information to develop the L1 adaptive controller and any other uses on the team that people might have for it. We can discuss sensor placements and other pieces like that. And then following that, and then we'd provide that as in addition to the Unreal ROS environment, provide the JSB Sim model for the team to basically do testing on the simulated aircraft inside of that environment. The next piece would be to actually tailor a Guam model to the Volley 10. And I did get an introduction to our NASA point of contact there, the expert on Guam model. I do need to follow up with him to find out exactly what the details would look like to get to go through and actually modify the Guam model to actually fit this aircraft. I do remember there are functions in the Guam kit they gave us to be able to do this, but it's going to take a little bit of time to go in and get those to actually match the performance of the aircraft. And then next steps is really work with all the various academic partners on the team to actually make sure do software in the loop testing with the ArduPilot in preparation for additional flight tests. So expecting that to be, again, another 6 months, and hopefully following that, actually move out and perform actual flight tests. And kind of the initial discussion with members of the team is that something that we could probably do in the ballpark, 18 months to 2 years away time frame. And there's a few thoughts on how we could do this. We of course need to do perception and mission processor payload development integration. You can look on the bottom here of the Volley. It holds it's got a small little docking plate. I've got a little more information coming up on where we could put a small mission computer in, as well as a sensing payload. And I'm developing one already that I'd make available to the team if that would simplify things and it meets the team's needs. Integrate that in, and then we'd have to come up with some collaborative flight safety checks processes to make sure that the autonomy pipeline is ready to fly, and then finally doing some flight testing in open air and near safe obstacles to actually test with and without the perception system in the loop. And then Of course, I really do want to make this available to the team to kind of test as much as possible. So if we get the extension and have time, I'd be very interested in ideas and suggestions from the team of how we can get more use out of this as a test asset. Inside this simulation, I kind of mentioned before, we use typically cesium supplemented with Maxar data. And you can see here at top, this is around Sparks, Nevada. And this is our office is right around inside this environment. The color data is point clouds collected from one of our ground systems, which we could use to add additional obstacles, trees, buildings, those types of things that don't show up in most data sets, but we've been able to capture with some of our systems and make that available as part of the simulation environment. And then stand up the environment and use this to kind of evaluate the full ROS pipeline coupled with JSP Sim and or Guam, Unreal, ROS, and then the components the team would actually bring on. I missed updating that one. I apologize. Next step, of course, is the hardware in the loop testing, as we kind of discussed. And a big part of that's going to be working with the team to identify what the proper processes are. SNC has our internal processes for pre-flight checkouts, but really needs to be a collaborative effort to make sure the team systems are also ready to fly. So discussions I have on that. And then, as I mentioned, 2 flight test environments. The first one primarily just for validate the flight checkout, completely open environment, no collisions, just safe open airspace to be able to fly around. And then the next place would be actually putting obstacles inside the environment that we kind of determine are safe-ish. There's only so much you can do, but putting something in where if we do crash the volley into it, hopefully it's not a complete catastrophic failure, but willing to accept a little bit of risk there. But the initial thought is provide with the obstacles mapped in advance, so the full autonomy pipeline knows the path, and basically it's a duplicate of what's been ran inside the simulation environments. And the full controls and decision-making pipeline is aware that where the obstacles are, and then the primary emphasis there is to validate that the perception is able to detect the obstacles as they fly without being relying on the perception being in the loop to actually decide to navigate safely away from obstacles. Once that's been completed, the next step is to transition to doing unmapped obstacles to really validate the complete pipeline and show that with perception in the loop, we can successfully detect obstacles and then mitigate around them. So to kind of help with the integration, as I mentioned a little bit ago, my team has developed a little autonomy test kit. It consists of 4 EO cameras, and I can provide kind of information on what cameras we have and how they frame rates and field of view and those types of things, as well as a VectorNav VN200 and NVIDIA Orin Nano. And we haven't actually flown this yet. Our first flight test is scheduled tentatively for November 13th. That could change a little bit depending on weather. We're getting that time of year where it's a potential issue. But it effectively bolts onto the bottom of the volley here. It's entirely passive at this point. It has its own isolated power system. We also have a Novatel RTK GPS on board in case we need a very precise estimate of its position and orientation. And all of that fits onto the belly here. And then this is just kind of to make available in case there is a desire on the team to develop a custom kit, which I certainly would understand, in case you need a little more processing power or you want to be able to share hardware across other systems. This is kind of how our current kit is outlined. So it gives you an idea of the kind of space constraints, and we have the bolt pattern on there as well. And again, I'm happy to make this available after. But if there's a desire to make a custom kit, that's definitely something we can discuss. One of the limitations is we can only about 5.5 inches on height before we'd need to start modifying the landing gear to get higher off the ground. But not much faster than I thought. In summary, SNC simulation environment is being adopted from the DVEPs to the volley, and then we're also kind of adjusting some of our internal development plans on the volley to support this effort. And that I'd like to say I'm thankful for everyone's attention, and I'm really also thankful there's an opportunity to be part of this team. It's really exciting work that you're all doing, and I really, really do see the value in it. And I hope I made that clear. And I'm happy to take any questions or any discussion, and then, yeah.
Okay, let's see who has questions. Thank you very much, Andy. My voice is echoing, so if there are any questions, go ahead. Sayan?
Yeah, thank you very much for this interesting talk. I was wondering if you could speak a little bit more about what type of verification opportunities you see here on all of these fronts. Actually, this vision-based auto landing is something very interesting, and we are starting to do some work in that space using simulators, of course.
Yeah.
And there is, of course, testing and validation, which you can only do with super realistic simulation or with field tests. But one of the thrusts in this project is focused on formal verification, which is offline static analysis of the system, or discovering the right kind of assumptions under which you can say something about, in what environments you can guarantee the system to work, right? So that's one of the directions. So given that the system development has progressed so much and you're already building and testing it in interesting environments, I'm wondering, where do you see the role of verification, or where can that add value?
So I'm more on the research side. So I have a team of people that guide on the verification piece. So I can only talk about it at roughly a high level. So I apologize for that. So the way, effectively, where that adds value is anytime you actually want to put a system into the field, the verification, especially on a manned aircraft, anything manned aircraft that's is strictly necessary to keep the aircraft in the flight. So the inner control loop, the central nav system, all of that, and flight controls are all DAL A. So you're 1 in 10 million chance of a failure. So it's very kind of critical. And then one of the points on there is it's also very costly to go in and do that validation and kind of verification of that pipeline, because it requires multiple code reviews. Typically, like on some of our systems, even some of our unmanned systems, will have 3 IMU, and I feel like I'm meandering slightly from your topic, but we have 3 IMUs on board that are all made by different manufacturers. We run 3 Kalman filters in parallel that are all stood up by different groups, because if we want different assumptions, even though they're basically stood up to the exact same requirements, they're all very different. And then we have decision-making software that basically kind of fits in between them. So, and that's kind of taking another level of each of those pieces needs to go through and line by line outline what the assumptions are of when it will hold, and then verifying that it actually meets those assumptions, and when it can detect when it fails, and then respond effectively, appropriately, to pull in an operator if possible. And on an unmanned system, what to do in the event of those failures. So yes, there's the verification piece is critical. I'm happy to get you on the phone with somebody from SNC who knows more of the details about it than I do. But
thank you so much. I'd love to learn more. Yeah, we can connect offline.
Okay. I would say on the machine learning piece, one of the approaches we're taking for doing safety and verification around machine learning, some of the methods we're doing there is trying to really narrowly define the machine learning as much as we can. So like you look at the auto landing systems there, for example, we try to do it for kind of the feature detection and correspondences. And then we try to build up with statistics from there the rest of the way, because then you can actually start to have some mathematical guarantees wrapped around it. But,
exactly.
Yep. Okay.
Thank you.
Yeah, no problem.
Hi, this is Kevin Wise from Boeing. So, excellent presentation. I really like this. This ties to the V&V topic a little bit too. Kind of like, maybe you can just briefly talk about the gap between the photo sim. I can't remember what your exact name, but the photorealistic sim that you talked about at the beginning, and then in your development. So if you're using that sim to do the training of your learning components, right? And then kind of the gap between that and the real sensors. Okay. So that's something that I know is very difficult to quantify today in the development of these systems. And I think this is going to be important in developing and certifying systems that do this, right, in the real world. So how do we address that gap in your planned work here? Did that make sense what I said there?
Oh, that made lots of sense, Kevin, and I appreciate everything that you I appreciate all the points you bring up, and I agree with you. And I also point out, I'm sure this is obvious to everybody on the call, but I pointed Lockheed a lot because they're a team member, and I didn't mean to exclude Boeing. Obviously, Boeing does amazing work here too in most of these areas. So, but getting back to your question, really quick, one of my advisors at OSU, his favorite expression was all simulations are doomed to succeed. And that really is kind of the problem I think you're getting at here is when we develop these simulation environments, we design how the simulators work, and then we develop them to work, we develop our systems to work explicitly inside that simulation. And it's all built on top of assumptions. And especially if you're geared anywhere towards real-time simulation, the assumptions of the sensors largely don't hold. So cameras, I feel like, are a little bit easier, but even then you can end up with the extrinsic or intrinsic calibration being off, obscurance inside the environment, atmospheric effects, and other pieces like that that can kind of degrade the performance. LiDAR's really another bad one to simulate it effectively. You need to cast the 2 million beams a second that your sensor can actually output. And at the systems we're using, the range is out to a mile away, which is computationally prohibitive in most cases. But to actually really model LiDAR well, you need to not do a single LiDAR beam. You need to do multiple beams for each beam, so you can draw a statistics about the beam that got emitted and what it likely hit and simulate multiple returns in other pieces. So in short, I completely agree with your point that trying to simulate anything and using it in verification is going to kind of be inherently challenging. And when you extend that to machine learning systems, where you're then using the simulation environment to train a system you intend to deploy out in the real world, I definitely think it gets more complicated. I think to talk to Georgia Tech, the professor from Georgia Tech, and I apologize, I've forgotten his name again, is definitely at least
Evangelos.
Yeah, sorry, yes, absolutely. I was trying to remember his last name to be respectful, but yes, Evangelos is doing very exciting work in this space, and I would trust his judgment over mine as well as most of the professors on the team. But I think I think the correct answer is likely to supplement with real-world data during the training as much as possible, and try to supplement also the testing done in simulation with testing done in the real world. And testing a system, and I kind of think the approach that we kind of discussed internally having here of doing the simulation first, trying to take models that were currently being used for those platforms, and we know that they actually the same autopilot can work to control that flight model as the physical system is a good starting point. And then after that, taking kind of a progressive step where you can wean in the complexity of the environment and do kind of a lower risk approach where at first you're doing flight tests in a safer environment, but now you're incorporating real sensor data to evaluate how they perform. And then internally at SNC, one of the things that we're doing is, for example, we have our radar systems and other landing systems and differential GPS where we can get the position and orientation of these aircraft and other systems with very high accuracy and confidence. We can use that as kind of a baseline to test our other systems out that were brought up in the simulator to show that they are actually matching those performance, and we can fly based on trusted systems and then gradually bring in the systems that were developed in simulation and compare them against those pre-existing sensors to kind of wean off of them over time. Hopefully that addressed your question.
Yeah, are you going to be visiting Illinois in a couple of weeks when we have the meeting there?
I will be. I'm only able to attend the first day though.
Okay, good. I look forward to meeting you there. Thank you.
Yeah, no, it sounds great. I'm looking forward to it also.
Andy, you said you graduated from Oregon State University?
I did. I was under Jeff Hollinger, Con Toomer, Bill Smart, and Julie Adams.
That was mechanical engineering?
Robotics.
Robotics.
It's now their Chorus Institute, but it was, they didn't have that stood up when I graduated.
Nice. Belinda is also coming for our review. Belinda Button, you know her?
No, I don't.
She was the head of mechanical engineering there for 10 years. Then she went into administration of the university. Okay, you'll see her here then.
Wonderful.
Yeah, thank you. More questions for Andy?
Since there are a few, Kevin, sorry, did you have a question?
Oh, no, see, I was just going to kind of talk about this meeting that's coming up at Illinois. It would be very valuable, I think, Naira, if we had some time just to discuss things, you know, versus having just briefings and not letting this team interact. So I'm hoping that in your agenda that I have a bunch of questions that I think would be better talked about in person than, you know, over the internet, you know, with regards to this kind of approach and what we're doing here. So I'm just hoping that, I just wanted to inject that. So when you're planning that agenda, you know, let's not make it just one briefing after another. And on that first day, let's get to allow the team to have some time to interact. Okay, thank you.
We do have coffee breaks and
I don't mean coffee breaks. I mean, really have an hour to talk. So when we want to ask questions, really have time to spend answering these questions. In particular, you know, Louis Shaw's work that we saw a couple months ago that talked about this error correlation and training learning components. You know, that kind of opens a question as to how we show the safety aspects in learning components that are trained with sims. And then when we get to the gaps between real life, so we need to talk about this. I think this, all the work here significantly, you know, it's all significant towards the certification of these things. And this is what the goal of this project is trying to get at that. So I think we need time to take a step back and say, what have we learned from all these people, all the participants in this team over the last year, and, you know, reflect on our ability to accomplish the mission of this project. Okay, over.
Kevin, that's brilliant point for NASA to extend it for another 5 years. So not just do 3-year rush project.
Let's see, I can clearly see that this work is ongoing. There's, you know, just like Andy said, lots of work at all the companies on addressing this. You know, we have a significant effort in the KC-46 program where the Air Force wants autonomous refueling. And you know, we have a lot of Hughes experts coming in, and this whole thing about, you know, using simulations to train and, you know, being able to dial in scenarios into these simulations quickly to allow you to use scenario-based testing in your evaluation certification. There's just all kinds of challenges here that still need to be addressed and then talked about. And then when we do that, how does that really prove out the system? You know, these kinds of things. This is a very worthwhile project that NASA's funding here. So, okay, thank you.
Thank you for all the compliments. And there is really lots of work happening. You see these monthly seminars, but like every Monday morning, we meet with Lockheed Martin and Louis Shaw just purely to talk on the certification thing. And once we invited Andy to talk, once we had Evangelos, but it's a meeting of Louis Shaw, this Chris Elliott from Lockheed and our group. We dive deep into the certification challenges. If you want to join the Monday morning meetings, we can maybe invite you. So we have lots of other calls besides these monthly Friday seminars in between different groups, different teams. Iris team is always in touch with us on their Guam model that we're kind of working through the simulation environment. Indeed, we're addressing very important, valuable problems. We're happy to do so. And I think we're worth the funding to be extended for another few years to really have the impact. And that has to go already from the advisory board, the message to the NASA maybe to make it happen.
Very good. Thank you.
Thank you. I really look forward to hosting all of you here, and we'll try to a little bit play with the agenda to make more room for this type of interactions and chats. Cyan had a good idea he put in the chat. We right now had back-to-back and then coffee breaks, lunches, poster session. From 4 o'clock onwards, we have poster session that you can use for this type of interactions and discussions. All the talks end at 4 p.m. and then there is poster session, then the dinner is at 6. And it will be all catered at University of Illinois. Catering will be whole day in the same room, up to the dinner included, up to 9 p.m. The room is booked for us. So the dinner time can also be used for interactions and so on. I just planned that way. Originally, I was thinking to go out for dinner, but then we thought it's better to stay in the same place and to maximize the time instead of leaving the room. So really
A
look
good idea.
forward to everyone. So are we done? So we close the room. No more questions. 1, 2, 3. Okay, then thank you very much, Andy, and really nice to see you. And hopefully we meet all in person in 2 weeks. Petros, you wanted something? You turned on video. No?
No.
Okay, thank you. Bye. The
Thank you.
recording will be posted. Thanks. Bye.